good GD&T people. This is video 2 of a series meant to address a big question I have about the GD&T system, in which you'll see that I'm going to cover a lot of ground that leads me into some rather expansive conclusions that have changed the way that I make drawings and how I think about GD&T. And this is always with an eye on keeping things simple, avoiding situations where we're imposing false requirements onto our parts, avoiding contradictions and inaccuracies, okay? Making our tolerances match very closely with the functional requirements of our parts. A lot of that has to do with the datum features, right? Datum feature selection based on the way our part locates to the other parts of an assembly. So up to now, we've been mostly looking at this blue part here, which we can call mostly circular or rotationally symmetric. And then, as we saw before, the blue part is going to be used as the base of this subassembly, which in turn is going to be installed onto this gray plate, which I'm showing as being just a detail area of a larger part you'll have to imagine. All right, so the blue part sits flat on the bottom surface of the pocket, which is a self-evident 3DOF primary datum feature. And then it locates into the gray part with a close-ish cylindrical fit around the outside diameter, a clear 2DOF secondary datum feature. And this is the version of the blue part where there's a pin in the gray part and a corresponding close-fitting slot or notch in the blue part. So in this blue part, the notch is a clear and classic 1DOF tertiary datum feature that constrains the part in rotation. Clear and classic, yes, but this is not really what these videos are about. What the videos are about is what we do when there is not a clear datum feature, providing some expected constraint, like this version of the assembly we started with today, where there's no pin in the gray part, no notch in the blue part. So we've lost our tertiary datum feature, and we no longer have the full 6DOF of constraint. But fortunately, as we talked about in episode 1, the standard anticipates this, and is 100% clear that this is not a problem for us at all. For a part with a cylindrical primary or secondary datum feature, like our datum feature B here, we can just leave out the tertiary datum reference. For instance, in the feature control frames of the 290 diameter screw clearance holes, or for this 1-inch diameter feature. And you can read all about that under section 4.10.3, which is 7.10.3 in the 2018 standard. And you can see examples like figure 4-8, which is 7-14 in 2018. And that figure looks a lot like this part. One additional thing we get recommended we do is to label these axes, X, Y, and Z. It seems to provide rotational direction, even if there is no rotational constraint. And it helps us to identify a datum reference frame. That's fine with me, although it is a pain to draw and fill in the arrows. Even though this is really clear in the standard, I see different things being done out there in my world. Pretty often, I encounter drawings like this one, where a designer is trying to force one of the holes to be a tertiary datum feature. So in that last video, I tried to show how this is unnecessary, doesn't really accomplish anything, and ultimately just leads to goofy things like there being 2 callouts for these 2 identical holes. Especially since we are armed with that 4.10.3, and we have this cylindrical secondary datum feature, there's an easy prescription for this one. You don't need this tertiary datum reference. Just leave it out. Well, with this idea that under these conditions, it's not necessary to have datum references that would constrain all 6 degrees of freedom, the standard is giving me a glimpse of something greater, okay? They've opened the gate a small amount, and I want to see where the path leads. And for me, this is all tied up with this idea of functional datum features, discussed in 4.15, which I take very seriously, probably expansively, beyond what is written in this section, as you're going to see. Because everything in GD&T works better when the features we identify as datum features are also the features that actually locate the part in assembly. As soon as we try to fake it and choose non-functional datum features, we start to get into trouble. But if you believe that you must always have datum features that add up to 6DOF of constraint, then what do you do when you have a part that is not fully constrained, does not have a functional datum feature to provide that constraint? Maybe that lack of constraint is actually an important element of the design, like if we replace the screw holes on our circular part with slots. It's almost like the standard says, yeah, you're right, that is a problem, and gave us 4.10.3 so we don't have to invent a non-functional tertiary datum reference. Okay, now we're getting to the point of this video. What about parts that are not circular or have interfaces that do not have a cylindrical primary or secondary datum reference and therefore are not covered by 4.10.3? How many of us feel like we are compelled to find a tertiary datum feature somewhere on this blue part, or even just to make one up? The most common thing is that people are going to look to these edges that make up the 3-inch feature, or to a center plane of the 3-inch feature to use as a tertiary datum reference on the whole callouts, etc. There are actually several ways that one may attempt to do this, but they all have the same problem, which is that these ends, this width, is really just a clearance feature and not a locating feature in this assembly. And so they all run into trouble. And I see this pretty often. We end up looking to more and more elaborate solutions to these problems. But they never seem to resolve the contradictions. And here's another thing, unnecessary requirements that we get from using non-functional datum features. It's going to take me 2 of these episodes, I think, to explain all the examples I want to show you. At first glance, this is a long detour, but I think it's important to run some of this to the ground in pursuit of the main point, which is to get an answer to my question. If I don't have a functional datum feature, and if the use of a non-functional datum feature would result in an inaccurate depiction of geometric requirements, must I have a datum feature at all? This episode and the next are going to deal with, I guess, the middle part of that question, where we look at how the use of a non-functional datum feature can create false requirements. And practically speaking, the false requirements can result in bad parts passing inspection or good parts failing inspection. All coming right up. Let's get into this rectangular part issue. Can we make some of the same moves or assumptions that work for us with a circular version of the part? All right, so this blue part still sits in the bottom of a pocket in the gray plate in such a way that we have surface features that are self-evident 3DOF primary datum features. So that's really similar to the circular part. Then, the pocket being rectangular, we have a locating fit on the long edges of the pocket, which to me looks like a 2DOF secondary type of constraint. MMB modifier for sure. And then the pin is back, okay? So we have this notch as a tertiary datum feature, locating the part on the pin, MMB. Does it seem like this part is sort of like an unfurling of the circular part? It has a lot in common with the circular part. Maybe you can say it has similar DNA, but the differences really set it apart in some interesting ways. In both of these interfaces, we have the flat surface primary datum feature. On the rectangular part, it's coplanar, a 2DOF secondary datum feature of size, and a 1DOF tertiary datum feature of size. The difference is the degrees of freedom that are constrained by the secondary and tertiary datum features. So if we have a look at the drawing, there's a relief across the bottom now, so the datum A feature has to get coplanarity. No problem. The datum B feature is now a dimensioned width, resulting in what will be a secondary centerplane datum that constrains the part in one rotation and one translation, compared to the circular part, which had a secondary datum that was an axis and constrained 2 translations. And our datum C feature, while still a slot or notch, constrains us only in the one last translation, whereas in the circular part, the slot was a rotational constraint. Okay, so there's some similar DNA to the circular part, but it would have this different kinematic function. There is another thing we have now with the rectangle that we didn't have before with the circle, and that is that we now have this length, 3 inches. In this assembly, there's a large amount of design clearance on both sides. So in my drawing, I want this to be a loose tolerance feature. And to make all my points, I have it at plus or minus 60, which is quite loose for a part made on a mill. And then I think this is all right. With the vertical center line, my intention is to depict the center plane of the 3-inch width as being nominally located on datum C. And then I can't help myself. I think LMC is the right call out in this case. If we were thinking about fit, it would be MMC. But we're not worried about fit because there's a ton of clearance. The LMC callout does something different, which boils down to preserving the wall thickness between the screw clearance holes and the edges of the part, which seems like pretty much the main function of those edges if you think about it. They provide a good seat for my washers up on top, and they give some width to the surfaces on the bottom. And so with 0 position at LMC, the idea is that when this feature is at its smallest, 2.940, it must be perfectly centered on the notch and also perfectly square to datums A and B. But the wider it gets, the position tolerance increases in a 1-to-1 sort of way. So at 3 inches wide, it has 60 thousandths of position tolerance. And all the way at 3.060 wide, it would have 120 thousandths of position tolerance. Anyway, cool call out. I love a good use of LMC. All right, so let's do with this part what we did to the circular part and ditch the pin in the base plate. And with it, the notch in the blue part. Now, when we place the subassembly into the pocket, it's going to locate on the long edges, but then it will be free to slide left and right, won't it? But as long as the distances between the screw holes in both the blue and the gray part are controlled, we should be able to make this work as an assembly. And that is, for whatever reason, we're content to scooch the subassembly left or right a little bit until the holes line up. We could even say that the sliding back and forth could be an element of the part's kinematic design. But the way I have this, you can see that even at the most extreme positions, there's still a lot of clearance on the ends. But let's not worry about the slots for now, and go back to a rectangular part with regular screw clearance holes. This is drawing GD&T Guy 00614. So now we have a problem because we don't have an obvious functional tertiary datum feature anymore now that we lost the notch. Remember, 4.10.3 tells us that we may not need rotational tertiary constraint, like when we had a cylindrical secondary datum feature. But now we have a centerplane secondary datum feature, and we are free along one of our axes, not in rotation. All right, well, there's still quite a bit of this that we can make sense of. We have our 2x coplanar datum A feature, great. And we can use that to establish our datum B feature and control that for orientation, also great. How about these 290 diameter screw clearance holes? We can give them position in A primary, B secondary, and I contend that will control them as a pattern, orient them normal to datum A, and position them on the datum B center line. So far, so good, but what control is there relating these holes to the other features on the part? For instance, the 1-inch diameter feature and the edges of the 3-inch width. Well, let's look first at the callout for the 1-inch diameter feature. This one has a positional requirement in that datum reference frame A primary, B secondary at MMB, which is exactly the same datum reference as we are using for the 290 holes. On the 3-inch width feature, again, I have position, and that same A primary, B secondary at MMB datum reference. There's no tertiary on any of these. But what I am hoping to do with these callouts is to bring into effect simultaneous requirements, which we touched on in the first video, and which we'll get into quite a bit more here. Simultaneous requirements is explained in 4.19 in the 2009 standard and in 7.19 in the 2018 standard. This is all in the datum reference frames section. And then there's a follow-up bit in the section on position tolerances. There are also some good illustrations. So these are just a few paragraphs buried kind of deep in their respective sections. And so it would be easy to nod your head as you read through simultaneous requirements, but not see it as a huge deal. I, on the other hand, do think of this as a huge deal, in GD&T anyway, with implications for many, if not most, part drawings. I thought hard about whether and how to include simultaneous requirements in the actual title for this video series, because it's such a central part of my big GD&T question and my conclusions, as you'll see. Let me start to show you how I think this applies. And so in the interest of being thorough, let's go all the way back to our version of the blue part that's circular and has the notch that provides tertiary rotation control. On the drawing for that part, we have datum features A, B, and C identified and related to each other. And then the call out for the 2x 290 diameter screw clearance holes has a position tolerance that references A primary, B secondary at MMB, C tertiary at MMB. This would imply a gauge like this, with some nice simple MMB datum simulators. And then there are some special gauge pins at the virtual condition size of the screw clearance holes. Now this would all have to go together simultaneously, right? With the two gauge pins in place at the same time. Well, what if we have a situation like this? And I'll exaggerate the size of the datum C feature to make the point. Now we have quite a bit of leeway to rotate this part in the gauge. What if that allows me to insert this gauge pin into this hole, but now I have interference on this pin? It won't go in. How about even if I'm able to pull the one pin out, then rotate the part in the gauge all the way to the other side of the datum C feature, and now I can get this pin in, but not on the other side. It's a failed inspection. And that just goes back to the way we specified this as a pattern of features. It's not just two holes with independent relationships to the datum reference frame. It can be treated as a single feature with a single requirement. Okay, so what about simultaneous requirements? Let's say for some reason that I've decided I'm going to secure this pedestal subassembly with two different sizes of screw. So in the blue part, there will be two different sizes of screw clearance hole. Same as before, we might expect that the drawing would identify the datum features A, B, and C. Only now with this one, we have two different screw clearance holes with two different dimensions. There's no way to say 2x because they're two different size holes. Well, with simultaneous requirements, it actually doesn't matter that these are two different callouts for two different size holes, or even that there are two different tolerances. They get treated as though they are the same requirement, a simultaneous requirement. This thing where you can get one pin to go at a time, but not both at once, you can't do that here either. So here it is, simultaneous requirement. Unless we explicitly say otherwise on our drawing, multiple tolerances for multiple features, all over a part and drawing, can be considered as a single pattern, a single requirement, in which you cannot translate or rotate the part mid-inspection, like if you had an MMB datum reference. Okay, now it only applies to position and profile tolerances, and the features have to be located using basic dimensions. And importantly, to apply simultaneously, the tolerances need to have identical datum references. So identical datum precedence, and identical modifiers. This figure 4-39, which is 7-46 in 2018 standard, is going to be really important to me in a few minutes on this video, okay? Because it shows how features controlled by profile callouts are also brought into simultaneous requirements, along with the features that are controlled by position. Figure 4-40 is going to be relevant even sooner. We'll get to that too. 7.5.4.2 is in the section about tolerances of position and kind of completes the thought of what I was just showing in the last illustrations, specifically on the topic of MMB datum simulators. But it presents it in this interesting way, telling us that anytime we have multiple features like this with position or profile tolerances having the same datum reference, we have this choice to make, where if they are separate requirements, we have to write sep rect under the callouts, because if we don't, they are considered as a single pattern of features. And then figure 7-54 shows a part, quite a bit like the blue part we've been looking at, that has two different sizes of holes and decides to call them separate requirement. And in so doing, communicates that now for this inspection, we only have to do one pin at a time. If we're on simultaneous requirement, we have to be able to install both pins at the same time. If we are on separate requirement, we do one pin, we remove it, we shift and rotate the blue part if we need to within the confines of the datum simulators, and then we do the other pin. This could make sense if we were going to only ever do one of these screws at a time, either the 1/4 inch or the number 8. But it is interesting that the default assumption, and this is a good and telling thing, I think, the default assumption is that the two holes and all the datum features are related to each other as elements of the same interface as they are here. Okay, but what has happened every time you have seen a pin and a notch so far in this series? That's right. Next, let's talk about what happens when we say goodbye to the notch. So now we're looking at a view of a blue part that does not have the tertiary rotational constraint that came with the datum C notch feature. It does have the two different hole callouts for the two different size holes. And notice that both of these hole callouts have the identical datum reference A primary, B secondary at MMB, and no tertiary. On an inspection gauge, would this be simultaneous, both pins at the same time? Or can I do one and then the other? Well, remember in the last video, episode 1, how we talked about a similar situation? Except in that one, the two screw clearance holes are the same size. And we talked about how these holes, the way that they're called out, are not just individual features that each have their own relationship to the datum reference frame. No, they are a pattern of features. And so you couldn't have a situation like this, in which the holes were each individually well enough located to the datums, but then not co-located to each other as a pattern of features within the tolerance. So when we look at our drawing with the two different size holes, the question is whether we can treat these two holes as being the same pattern of features. Well, that's exactly what simultaneous requirements says. And these hole callouts meet all of the conditions for simultaneous requirements. Position tolerances, located with basic dimensions, and I include the center lines in that, and identical datum references. So now you see it, folks. A simultaneous requirement applied to features of an interface with a datum reference that provides fewer than 6 degrees of freedom. Parenthetically, if you go and look at figure 4-40 in the 2009 standard, 7-47 in 2018, you'll see it applied with a 4-DOF constraint, provided by a cylindrical primary datum feature. Okay, and that simultaneous requirement extends by default to all of the features with that same A primary, B secondary at MMB datum reference, controlled by position or profile, which would include the 1-inch diameter feature here. And so would also bring in this special gauge element, if you remember this one, that checks the position of the 1-inch diameter feature. Okay, because do you see? The position tolerance there in the upper frame has that exact same datum reference as the screw clearance holes and is considered, again, a simultaneous requirement. So as long as there's still one possible position rotation combo where all of these gauge elements can be installed, so all these features are within their tolerances simultaneously, then we're all good. When you look at all these parts and their respective gauges, whether the holes are the same size or not, there's still quite a bit of constraint building up, even in the parts on the right that do not have a tertiary datum feature. They're constrained well enough, anyway, to fully define the part, which is what we're after. Okay, so now that we're freshened up on simultaneous requirements, let's go back to this drawing GD&T Guy 00614 of the rectangular part with the centerplane secondary datum. You remember how I established a 3DOF datum A feature and a 2DOF datum B feature, but then I struggled to identify a feature that would provide the 1DOF translation constraint. So my idea is that maybe just like the circular part, there doesn't need to be a tertiary datum feature for this interface. And the idea is that I get there using simultaneous requirements, using basic dimensions, position tolerances, and identical datum references for the 290 holes and for the 1-inch diameter feature, at least for starters. If we imagine a gauge for this, it would have the datum A simulator, a datum B simulator made at MMB, and no tertiary datum simulator. And then you would have the virtual condition gauge elements that we've seen many times now for the screw clearance holes and for the 1-inch diameter feature. And as you can see in this section view, there's quite a lot of constraint building up in here, with these gauge elements all working simultaneously. But I do think we need to resolve things when it comes to the ends of the 3-inch width, now just hanging out in the open. Well, I said I wanted this to be a really loose tolerance feature, plus or minus 60. And that's just because there's quite a lot of clearance in the assembly, and I don't want to pay for precision. And all I'm really looking for is that there remain a reasonably thick section between the outer edges and the screw holes. So I'll tell you, without a tertiary datum feature, it feels a little strange to use position here on the 3-inch feature. Perpendicularity seems like more the usual thing. But perpendicularity won't get me to simultaneous requirements. So that's why I'm feeling like I have to go with position. I have the A primary, B secondary at MMB datum reference, so that checks out. It's interesting that I'm using LMC in the tolerance, but that's not the datum reference, so that should still be fine. I'm not 100% sure it's clear that the feature is centered on the vertical center line, the one with the section cut. Maybe you can see that I have some doubts about this drawing. Add to that the fact that we don't have anything like 4.10.3 to tell us that this is perfectly legit to leave out that tertiary constraint. But then again, I don't see anything in simultaneous requirements or anywhere else that says I need to have 6DOF constraint to make this work. But let me just finish the thought when it comes to this gauge, the 3-inch wide feature, and the LMC position tolerance. What I was thinking is that you could measure the size of the 3-inch width. I mean, that could even happen off of the gauge. And if it's good, we could put in all the gauge elements. So maybe what you would do with this is take straight edges or gauge blocks and make sure that the edge of the blue part is protruding beyond the edge of the gauge. I think this is either right or pretty close to right. The LMC gauge is a pretty tricky thing to nail down. But hopefully you can see that the intention here is to maintain those sections. Make sure there is enough material between the screw holes and the edge of the part. And to bring those edges, that width, into a simultaneous requirement with the other features in the datum reference frame, for which we have these other gauge elements, right? All of that makes me feel like I'm able to define this part fully without identifying a tertiary datum reference to constrain the part in that X translation. And I even drew in the little XYZ arrows, okay? That's got to count for something, right? But now have a look here, because I think I have something even more ironclad in this drawing GD&T 00615. To keep things exciting, I based this drawing off of the version of the rectangular part here with the slotted screw holes. But the real action starts here where these basic dimensions now show us the nominal positions of the edges. And one thing I like here is how we're now dimensioned off of the center line, just like the slots and everything else we're trying to be simultaneous to. And then I'm saying 2x profile, kind of hoping that this will be understood as applying to both ends, but I'm not sure it's 100% right. Still, it felt better than having 2 callouts. But look, I'm just teasing this drawing at you right now, because I'm planning to come back to it some more in the next video, which will be episode 3. Okay, where are we now in the big picture of my original question about GD&T, which is something like, if I don't have a functional datum feature to constrain my part in 1 or more degrees of freedom, must I have a datum feature at all? And even though I don't think this is made clear in the standard, the reigning idea sure seems to be that every part, or maybe every interface of every part, must be constrained in 6 degrees of freedom. And that constraint must be achieved by datum features. And if there are no functional datum features, we are meant to choose some other, hopefully convenient feature, even though it does not play a role in locating the part in assembly. Well, I disagree with that. I think functional datum features and simultaneous requirements are like the 1-2 punch that takes down that reigning idea. And I think the next logical question is, what if none of these edges is a locating feature? Do I even need to have a secondary datum? But this is still to come, because we have one more big thing we have to address in the next video. And this has to do with the issue of how strong is our 1-2 punch. We spent quite a while on this video showing how strong a punch simultaneous requirement can be. And now we have to show how strong a punch functional datum features can be. Because someone could easily say, GD&T Guy, why do you feel like you need to pick a fight on this? Just choose some datum features. What could possibly be wrong with that? But it's like I've said, I'm in this because every time we try to use a non-functional, non-locating feature as a datum feature, we end up applying requirements that do not match the functional requirements of the part geometry, or specify it inaccurately. And I've got a lot of examples of these. Things I've done, things I've seen. I feel like I need to run these all into the ground. And it's going to take me the next episode to do it. Possibly it will be tedious, but it seems to me to be necessary to the case overall. I'm underselling it. If you've made it to this point, and if you've enjoyed these 2 episodes, you are a likely candidate to enjoy the next one as well. Until then, this is the GD&T Guy signing out.